Now, we have another gas law that we call the ideal gas law. So far we've been looking at the combined gas law and standard molar volume and our ways of measuring pressure. Now we're going to extend into one more gas law called the ideal gas law. The ideal gas law is a law that covers what we call ideal gases, or gases that are not close to liquefaction. That means the distance between the gas molecules is very large, so they don't experience each other's volume, and there's no attractive forces between them. So they follow this gas law down here that PV is equal to nRT. You notice there's one pressure, one volume, one number of moles, and one temperature. The units for pressure in atmospheres, the volume in liter. The unit for mole is of course mole, and the unit for temperature is Kelvin. Atmospheres times liter cannot equal mole times Kelvin. So we have another constant in there. We have another multiplier in there, this constant R, 0.08206 liter atmosphere over mole Kelvin. And notice it has units on it. Those units are for crossing out and making one side of the equation's units equal to the other side of the equation's units. Now don't fall into the temptation of trying to plug something into liter, atmosphere, or mole, or Kelvin. Those units there in the R are not for plugging in. They're there for crossing out only, so that you get unit cancellation and the entire equation works out. Okay, remember that you must have particular units in this equation. You can't have torr for pressure or meters cubed for volume. You have to have it in particular units. Let's look at an example of how this law applies. If I read this problem, you'll see what is the volume occupied by 16 grams of ethane gas at 720 torr and 18 degrees Celsius. I go through and I remove each number and set it equal to a variable. Well, 16 grams is mass, 720 torr is pressure, and I'm recalling pressure needs to be in atmospheres. 1 atmosphere equals 760 torr, so I can do a conversion of 720 torr times 1 atmosphere over 760 torr. That gives me 0.947 atmospheres. I take out my 18 degrees Celsius, that's equal to temperature, and of course in dealing with gases, temperature must always be in Kelvin, so I converted that. Now, I write the equation that applies. PV equals nRT. How do I know that PV equals nRT applies here? Because there's only one set of conditions. There's no changes occurring, and you're not having initial pressure and final pressure, or initial temperature and final temperature. There's one set of conditions, so this is the only equation that can apply. If you have two sets of conditions, an initial set of conditions and a final set of conditions, well, that's a combined gas law, isn't it? Well, PV equals nRT is the equation that applies, and if I look at the problem, it says what is the volume, so I know I'm going to have to rearrange this problem and solve for volume. Volume is therefore equal to nRT over P. I go and I look and I say, okay, in this set of variables I'm going to plug in, I have pressure, 0.947 atmospheres. I have temperature, 291 Kelvin. R, I always have R. That's a constant. It's always going to be equal to 0.0206 liters times atmosphere over mole times Kelvin. Remember that constant always gets plugged in here. The last thing I need is N, number of moles. And if I look at the data that's given to me, I might have my memory jogged that I can always convert grams to moles using molar mass. Notice the formula for this molecule is given in the problem, C2H6. So I'm going to go ahead and get my number of moles from my mass, and I do it using this conversion. 16 grams times 1 mole over 30.07 grams. This gives me 0.532 moles. Now I'm at a point where I can do a plug and chug. I can plug in each one of my variables and then chug out an answer on my calculator. So I enter in 0.532 mole, 0.0821 liter atmosphere over mole Kelvin, times 291 Kelvin, and divided by 0.947 atmospheres. This is equal to 13.4 liters. Go ahead and try this problem. Pause the lecture and then press resume after you've come up with an answer. The first thing that you need to do when reading this problem is to pull out each one of the numbers and set it equal to a variable. Notice it says what is the pressure, so I put P equals question mark. 125 grams is the mass. You should have a little jog of memory there saying, oh yeah, I need to convert that to moles. And I see 3,960 milliliters equal volume, and you might have a little jog of memory saying, oh yeah, that needs to be in liters. And then 29 degrees Celsius, that's my temperature, and you should say, oh yeah, that needs to go into Kelvin. So I'm going to do all those conversions. 125 grams, I take carbon monoxide, has the formula of CO, which has a molar mass of 28 grams. So I convert that to number of moles. Volume can be converted from milliliter to liter by using 1,000 milliliter is a liter. Now, you may have used milliliter equal 10 to the minus 3 liter. That's good. And then temperature, I add 273, and that gives me 302 Kelvin. The next thing I need to do is to write what equation applies. So I write PV equals nRT. I need to solve for pressure, so now I'm going to rearrange my equation. I come up with P equals nRT over V. This is to a point now where I can plug in my numbers into the variables. So I plug in each one of these, and I come up with 4.46 moles times R. Remember, it's standard. You have to remember that constant when doing an exam. Temperature, 302 Kelvin, and 3.96 liter. I plug it into my calculator and chug out 27.9 liters. Go ahead and try this problem and resume the lecture after you pause to try it. So what is the temperature of 3.1 milligrams of hydrogen gas in a 34.5 milliliter container at 725 torr? I go and I remove each one of those numbers and set it equal to a variable. Temperature is what I need to solve for. What equation applies? One set of conditions for each type of variable. No changes are occurring. There's no initial set of conditions and final set of conditions, so I know PV equals nRT is the equation that applies. Now remember, for this equation, pressure needs to be in atmospheres, volume needs to be in liters, and number of moles is needed, so I'm going to have to convert milligrams to grams and then grams to moles. So here are my conversions. Notice for number of moles, we go milligram to gram. And then this might have been a little trick for you. For hydrogen gas, remember hydrogen comes as a diatomic molecule, so my molar mass would be 2 times 1.008 grams, giving me a molar mass of 2 grams. Sometimes students forget that. It's easy to forget. That gives me 0.00154 moles. For volume, it must be in liters, so I did a milliliter to liter conversion. And again, if you used milliliter equals 10 to the minus 3 liter, instead you would have come up with the exact same number of liters. Torr to atmosphere, you're going to have to 1 atmosphere is equal to 760 torr, and so we come up with 0.954 atmospheres. So now what I need to do, it says what is the temperature, so I'm going to need to rearrange this equation so that temperature is equal to PV over NR. Notice number of moles and R, the gas constant, are multiplying times temperature. So that means I need to divide by number of moles, and the gas constant over here on the right side of the equation, if I divide on the right with N times R, then I divide on the left with N times R. So that gives me temperature equals PV over NR. This oftentimes is a problem for students because they're not doing their algebraic rearrangements correctly. If you need help doing this, please ask me for help. So now all I have to do is plug in my values. These are the values that I have for PV, N, and R. Of course, R is always the same thing. Notice liters cancels out, atmospheres cancels out, and mole cancels out, and I come up with Kelvin, which is a temperature. And when I plug it in on my calculator, I come up with 260 Kelvin. If you want to express it in Celsius, you could have converted it to negative 13 degrees Celsius also. The last law that we're going to look at in this chapter is called Dalton's law, or the law of partial pressures. When we have gas mixtures, each one of the different gases is causing collisions, and a certain amount of pressure is due to that gas. What we find is that the individual partial pressures all sum up to a total pressure. We can actually measure the amount of pressure being caused by each component, and then when we measure the total pressure, the sum of those partial pressures will add up to the total pressure. An example of this is if you have the following partial pressures for nitrogen gas, oxygen gas, carbon dioxide gas, and water, what would be the total pressure of the sample? All you have to do is take the individual partial pressures, sum them together, and you get the total pressure. Now, make sure you do problems. It's going to be essential for you to try problems in this. Do the end of chapter problems, and the worksheet problems are posted also. There's a POGIL for the gases that you will find will take you stepwise through this if you're having any kind of trouble with the gas laws. Be sure and log on and do your online quizzes.